It's the second lesson in theory of computation. We will go on with non-deterministic finite state automata. Why do we need non-deterministic automata? Non-deterministic finite automata by their design focus directly and only on how to accept inputs. Therefore non-deterministic finite automata are easier to design than deterministic finite automata. While deterministic finite automata are used to implement on machines, non-deterministic finite automata are used to help people approach the problem more easily. Although they look different theoretically, these two types of automata are equivalent in power. Thanks to this feature, we can use non-deterministic finite automata when solving difficult problems, and then transform the solution into deterministic one. There are three types of uncertainty to use in NFA. The first one is additional outgoings edges. The second one is undefined outgoings. And the last one is arbitrarily transients. You can see all of these uncertainties at the following transition diagram. For example, look at the Q1 state. Therefore the system cannot find which one to choose when the user enters a symbol 1. To see the second kind of uncertainty, look at Q2 state. There is no definition for symbol 1. If the user enter a symbol 1 at there, the system cannot find any outgoing. And when you look at the transition between Q2 and Q3, you will see an arbitrary transition. Epsilon. Epsilon means that the system can switch from Q2 to Q3 at any time without waiting for any input symbols. We now come to the formal definition of a non-deterministic finite automaton. Definition. A non-deterministic finite automaton is a 5-tuple M equals capital Q capital sigma delta lowercase q capital F, where capital Q is a finite set whose elements are called states. Capital Sigma is a finite set called the alphabet. The elements of capital Sigma are called symbols. Delta is a function defined as Cartesian product of capital Q and capital Sigma. Epsilon goes capital PQ, called the transition function. Lowercase q is an element of Q. It is called the start state. Capital F is a subset of capital Q. The elements of capital F are called accept states. It's our first example. Capital A is defined with W words so that W is a binary string containing 101 or 11 as a substring. Here, because of the question, our alphabet will be binary. So capital Sigma includes 0 and 1 only. Then we should find the states. We can directly focus on 1, 0, 1 and 1-to-1 strings. We can design them as two different subsolutions, but if you can see, they have a common solution. When we design states, we can define their workings as follows. Q1 is the start state. Q2 means the first symbol is okay. It doesn't matter 1, 0, 1 or 1-to-1. Q3 means the second symbol is okay for 1, 0, 1 or directly pass for 1-to-1. Q4 means the last symbol is okay. Now we can run the NFA defined here for entry 0, 1, 0, 1, 1, 0. For the first symbol 0, we must start and stay on the Q1. But we have an option for the second symbol 1. We can stay on Q1 or move on to Q2. In this way, you can also examine the tree of possible transitions. A second example. Capital A contains the binary words W such that W has a 1 in the third position from the right. We solved this problem while learning DFA, but this one will be easier than the one in DFA. Again, we can focus to design solution directly. Remember, in the previous solution there was a concept used to mean whatever symbol comes in start and end states. We will use this solution shown on the right in this question as well. But we will only use it at initial state, because no matter what symbol comes first we need the last three symbols. Here the number of states is not important as much as at DFA. Q1 means both the initial state and the time elapsed state until the third letter from the right. Q2 means the third symbol from the right came. Q3 means the second symbol from the right came. Q4 means the last symbol came. So it is final. A equals 0 to the power of k such that 0 equivalent k mod 2 or 0 equivalent k mod 3. The string contains any number of symbol zeros. We can accept the string when its length is a multiple of 2 or 3. If we misunderstand the question here and create a common solution to these two problems, the following problem may arise: 00 or 000 . Then this wrong solution may mistakenly accept the following string: 00 000 00 000. In fact, this solution is the union of the two languages. A equals A1 union A2, where A1 accepts the strings when their lengths are multiple of 2, and A2 accepts when the length is multiple of 3. That's all. Thanks for listening.